Hello, this is Tom Sargent, and welcome to second year macro uh, with Alessandro Dovas. So I'm going to give a background lecture today about basic ideas that we're going to be that are going to run through much of the class, and I'm going to present them in as simple a setting as possible. So it's going to be a basic introduction to something that some of us call dynamic programming squared. And I'm going to present this in the simplest possible context. The first part, I'm going to use linear quadratic dynamic programming. And my starting point is going to be chapter 5 of RMT4 with Lars Lundquist. So that's going to be just plain dynamic programming. And the reason that I'm starting with linear quadratic is that linear quadratic dynamic programming is the one setting in which it's possible to solve Bellman equations almost analytically using linear algebra. And you'll see why we say almost. And that has a great convenience. And it's the reason linear quadratic dynamic programs are used widely in science and engineering and applied mathematics to solve actual problems, because it's a setting in which the curse of dimensionality is more or less controlled. We can handle large dimensional states. So the curse of dimensionality is put under wraps here. The other reason is that the calculations are transparent. Yet another reason for studying this is it's linked to optimal linear filtering, in particular the Kalman filter. The mathematics is basically identical, and the reason is because of basically duality and the Lagrange multiplier theorem. And we'll briefly touch on that, but I won't focus on it. Okay, so then my reason for focusing on linear quadratic dynamic programming is that it's going to open the door to talking about dynamic programming squared and time inconsistency of optimal plans. So we can give a modern version of this, and there's going to be a hint of what's to come even in this first lecture. So that's where we're going. So now, why are we interested in dynamic programming squared problems? Well, they're going to be in this class. They're going to occur all over the place as a way to approach Ramsey problems and recursive mechanism design problems. And we're going to see these throughout the course. And by that, I mean Ramsey problems are going to be optimal taxation problems. Where there's a government facing not just nature, laws of motion dictated by nature, but a bunch of best responses by a collection of private agents to the Ramsey planner's decisions that are going to impart a dynamics to the Ramsey problem that at first sight seem to violate any hopes of constructing a recursive representation of the problem. When Edward Prescott wrote his famous paper, right after he wrote his famous paper with Kidlin about time inconsistency of optimal plans, he wrote a second paper saying that optimal control and dynamic programming could not be used to solve Ramsey problems because they weren't recursive in the natural state variables. That's true, and we're going to see how they can be made recursive if you resort to dynamic programming squared. And Ed Prescott himself with Finn Kidlin are two of the early authors and founders of dynamic programming squared. And the second is recursive mechanism design problems. We're going to study problems in which there are incentive constraints that have to do with enforcement, imperfect enforcement. The Arrow-Debreu model assumes perfect and costless enforcement. We'll study models in which enforcement is costly and creates frictions and disruptions of marginal conditions that a planner would want to have. And we'll also have information problems where there's disparate information between a planner and agents, or between agents themselves within the economy. And so we'll study contract and optimal taxation problems with such things. And dynamic programming squared is going to be a key thing. And the reason we call it dynamic programming squared, there's going to be a Bellman equation inside of another Bellman equation. So some of the state variables in the outer Bellman equation are going to be value functions or maybe gradients of value functions that come from yet another Bellman equation. So we're going to see this idea applied in a variety of contexts. So that's where we're going. So our approach in this class is going to be to do a small amount of material fairly carefully. So for today and next time, I'd like you to look carefully at Chapter 5 and Chapter 19 of RMT4. And that's where we're going. So let's start with Chapter 5. And we're going to talk about linear quadratic optimal control. We'll go over this fast because you probably saw it last year. And just remind you of this and some beautiful equations. So here's the simple one that we'll start with. It has a name. It's called the optimal linear regulator in applied mathematics. Regulator. And here's the deal. There's a state vector xt. It's an n by 1 state vector. There's going to be a vector of controls. Let's say it's k by 1 that are chosen at time t. And there's a criterion function that the person who sets these controls wants to minimize. So here's the criterion function. It's going to go from, I'm not going to discount it. It's going to be undiscounted. There's going to be no randomness in this first version. So R is a semi-definite, positive semi-definite matrix. And U is a semi-definite matrix. And so the simple version of this problem is that R, by that I mean it's semi-definite, and Q. But these can be relaxed. And I must say that they must be relaxed for most economics problems. and they can be quite readily. Okay, so there's the objective function, and we have a decision maker who wants to maximize this. And what is the person going to choose? It's going to maximize by choosing a whole sequence of u's from t equals 0 through infinity. So this problem's not complete yet because I haven't specified the constraints. Well, there's going to be a sequence of constraints that is linear law of motion that maps a state today and a control today into a state tomorrow. So A and B, that's an n by n transition matrix, and B is an n by k vector of controls matrices. And this problem still isn't complete. We have to add that x0 is a given state vector. So now the problem is well posed. Okay. So there's a sequence of these. There's one transition law for each date t. I'm choosing to do this in discrete time. We could have done this in continuous time. And there's beautiful mappings between the discrete and the continuous time formulations, which I can point you to if you're interested. Okay, so our problem is formed by a four-tuple. So a set of matrices that are appropriately conformable define an optimal linear regulator problem. And we're not discounting. We'll discount in a little bit. Okay, so there's going to be two ways to solve this. There's the undergraduate way, which is perfectly respectable and in some ways first class. That way, what we would do is we would put a sequence of Lagrange multipliers on, I'm going to be a little vague here about the dating here. We're going to put a sequence of Lagrange multipliers. I forgot whether that should be a t or t plus 1. We'll figure that out. We're going to put a whole sequence on this, and there's going to be a multiplier right here. So for each, and this is a vector, we put a sequence of Lagrange multipliers on that, and then we formulate a great big Lagrangian. We maximize with respect to u's, we minimize with respect to the lambdas, and do the usual thing. And we cross our fingers, and we hope this is okay, even with an infinite number. We'll have to take care of infinity right here. We'll have to be very careful about that, and we'll talk about that when we talk about stability conditions. So stability conditions are going to play a role a little later today. Okay, that's the first way. The second way is to use first year NYU macro and to formulate this as a dynamic programming problem. Okay, so for the next 10 or 15 minutes, we're going to formulate the dynamic program. Okay, so we'll formulate this now as a dynamic programming problem. So dynamic programming is all a big bluff because the whole approach is to guess and assume you know the answer to the problem even before you solved it. So we're going to make a guess. Well, so when you do dynamic programming, you always say, you begin with the word let. That's always the first word. So we're going to let v of x actually we'll put an x0 be the optimal value of the problem after we've solved it. So after we've solved this problem, we've maximized out all the u's, and we've chosen an infinite sequence of k by 1 vectors of u's. Actually, technically, what we've chosen, if we go back here, we've chosen UTs and states for t equals 0 through infinity. We've chosen an immense amount of objects. And once we substitute those optimizers in, call those the optimizers, we've substituted all of those in for t equals 0 through infinity. After we've done all that, we get this value function v of x0. So that's the answer to the problem. Okay, so we're going to let v of x be that, and then we're going to use the we're going to assume we know that, and here we're going to assume something else. For this problem we're going to make a guess. So for most so what's our approach going to be? Then the next approach, if you do dynamic programming, we're going to write a Bellman equation, and the Bellman equation would look like this. That's just u for today, and we write x prime r x. That means today. Plus u prime q u. That's today. And then we add in tomorrow's value function, v of tomorrow. And then we just solve basically what's a one-period problem, where the prime means tomorrow here. What we do is we use some reasoning to show that the value function is going to have to satisfy this functional equation, where it's the same value function on a right-hand side and a left-hand side. So whatever the value function is, it's going to have to satisfy this equation. And this of course, is the Bellman equation. So Bellman and Wald's reasoning was there had to be an equation, something like that, when they invented sequential analysis and dynamic programming. But problem here is this is a hard functional equation to solve in general, and often the only way to solve it is to get a computer involved in a heavy way, and to make approximations to what this value function is. But for the linear quadratic problem, we can make this guess that the value function v of x is a quadratic. That's the guess. And the guess is inspired by, well, what inspires the guess? The guess is inspired by it's a linear constraints, and it's a quadratic objective function. And that's what our justification for the guess is. If we're pressed, we're going to make that guess, and then we're going to verify. That's the whole thing. So that's where we're going. So this turns out to be a good guess. So we write down this problem. We're going to maximize u again. So now we're maximizing only one period. And we write this down. I'll just do this. And then now we're going to use a trick. Instead of x prime, I'm going to actually substitute in, put my prime there. That's what my Bellman equation looks like. And the key thing is now there's a p on the left-hand side and there's a p on the right-hand side. So now, but everything inside is quadratic on the right-hand side. So I can just apply standard formulas from linear algebra, and I can get first-order conditions here. So the first-order conditions for this become, and these are famous first-order conditions. So these might start reminding you first order conditions you got from a very different problem when Cogley was teaching you econometrics last year. So then if we just, that's the first order condition. We cross our fingers and hope those necessary conditions are also sufficient. They will be under appropriate conditions. Notice, by the way, I haven't said much about A, B, Q, and R. I haven't said that A is a stable matrix, for example. I haven't said any of that yet. So if we solve this, we get this formula. It's a beautiful formula for the optimum decision rule. But it's got an unknown P. So what then we do is we're going to substitute this decision rule in here everywhere U appears and rearrange. And if we do that, I'm actually going to rewrite this. I'll come back and rewrite this equation. I'm going to write this minus fx. Oops, there's an x there. I left the x out. So what this is, this tells us where f is. That's f. That tells us our optimum decision is a linear function of the state. I'm going to substitute that big formula in to the right-hand side and rearrange, and I'm going to get a quadratic equation in x on the right-hand side, and it's going to, after rearrangements, I'm going to get this equation, which is a famous equation. Okay. So this equation has a name. It's called an algebraic Riccati equation. And I have a number of very large, very big books about how to solve this equation and how to solve it fast. Because in industry, people solve this over and over again, and there's big returns to fast ways of solving it. But how might we solve it? From first year macro, we might just iterate on the Bellman equation. And when I say solve it, this is a matrix quadratic equation in P. And say a couple things about it. Well, you know from high school algebra that quadratic equations and scalars have multiple solutions. So this equation is a quadratic equation in a matrix, so you might guess it has multiple solutions. And it does. We could count them. It's got many, many solutions. So, but there's only one of them that's the correct solution for the Bellman equation. And given that we put R and Q both being positive semi-definite matrices, it's kind of natural to want, I'm going to put in quote here, this is partly an implied and it's partly a want operator. We want P to be positive semi-definite. And it turns out, while there's multiple solutions of the Riccati equation, there's a unique positive definite solution. And I'll show you how to find it. The way you find it is you just copy the equation, copy it. I'm going to copy it because I don't want to make my notes too messy here. Oh, I see a mistake. That's a B. That's a PB. That's right. Okay, so I've copied it. Okay, so now I'm going to put a J on the right-hand side, meaning the jth iterate, and I'm going to put j plus 1 on the left-hand side, and I'm going to start off from p0 equals 0. So this equation up here is called the matrix Riccati difference equation. And under some sufficient conditions, I'm going to say beautiful sufficient conditions, iterations on star starting from any p0 greater than or equal to 0 converge to p, the solution of dagger. The solution of dagger that we want. And just a little side thing is the sufficient conditions are not Blackwell's conditions A and B for T of P to be a contraction. Because if we call the right-hand side of this T of P following Blackwell, not a contraction. So it turns out you have to use a different kind of mathematics. So instead of Blackwell, we use Leuenberger and Calef and ... for sufficient conditions. I might touch on those later. But okay. So that's it. So the punchline is we get a value function, and we get a decision rule that's a linear decision rule. Okay. So let's make a couple little remarks. So what you could ask is, well, first thing is, this equation star is just kind of remark. These value functions, you could ask, so let's ask two questions. One, does star, or I should say do, have to speak English properly, do dagger and star remind you of anything? So this is free association. And, if you were in Cogley's class, you would say, yes, they remind you of something. And then the second question is, are dagger and star the same as what Cogley showed you? And from memory, you might say, namely, the Kalman filter. You might say, yes, but you'd be wrong. The answer is no, unless you turn yourself upside down and read backwards. Maybe I'll explain that strange remark. And then here's the third thing is, does star I'll call this thing VJ X0 equal minus X0 prime PJ X0 have any meaning? And the answer is yes. It is the optimal value function for a finite horizon version of our problem, where we replace, I'm going to be lazy and sloppy, summation t equals 0 through infinity with t equals 0 to j. That's what it is. It's a horizon problem. Okay. Okay, all those things. So we can go over fast about the discounted linear quadratic dynamic programming problem. So what is that? Well, we're going to replace, here's the way this will go. We can go fast. We're going to replace the objective function with this, as we usually do in much of macro, much of I/O, much of finance. We're just going to slip a beta in here. And then what you can verify is that the Riccati equation now is going to become, we're just going to have to put some betas at appropriate places. We derive this exactly the same way. You see where I'm putting the betas. Oops, I need another beta. Oh, I put the beta there because I put the square there. You see why I hesitated. There's my Riccati equation and my optimum decision rule. Okay, so that's it. So iterations on this. And there's a trick. I'll tell you, there's a computational trick. I'm going to say there exists a trick for converting this equation into an undiscounted Riccati difference equation. That's a valuable thing to know that exists. I might later point you to some places where that's done. Okay. Very good. Okay, so here's what I want to ask you to do on your own. This is beautiful. It's remarkable. And it's going to be, I want you to read about the stochastic optimal linear regulator dynamic, the stochastic linear quadratic dynamic programming problem. And so the version there is, we just do the following thing. I'm going to tell you the punchline, and you can read the reasoning. I'm going to put E0 is going to be the mathematical expectation. I'll use the discounted version. So now I'm going to turn on some noise. And the noise is going to be a special part, a special kind. It's going to look like this. Here we go. I'm going to have a volatility matrix CT, C, going to be a constant, and I'm going to put a noise here. And this noise, it's going to be IID. I have some freedom on how I specify this, but what's typically done is this is normal zero, a standardized normal vector. So this is now an n by p vector of noises. So now we go back to this drawing board, and we want to choose. We want to maximize this thing. I'll call this star again. I want to maximize star, and I want to choose ut xt plus 1. But now I have to respect some information constraints. I want ut and xt plus 1 to be measurable with respect to, well, a couple ways to write it. I'll say the history, jt, which is going to be a set of random variables that are measurable with respect to xt minus 1 all the way back down to x0. I'll put it that way. So they can only depend on the history. So here's what happens. We guess again. We're going to guess at an optimal value function. We go through our steps of doing dynamic programming. And we always have to start with the word let. So I'm going to let v of x0 be the optimal value function. And I'm going to guess that it's x0 prime p x0. And now there's going to be a constant v. So the difference between this guess and what was before. So here's the astounding thing I'm going to also guess. I'm going to guess that first. I'm going to guess that p is the same as above. That means it does not depend on C. The fact that I turned on the noise is going to have no effect on P, I'm claiming. And I'm going to guess that, therefore, F, the decision rule, does not depend on C. And I'm going to guess that only D depends on C. And these things have a name. These are called the certainty equivalence principle. And this has a long history. In economics, this was noted by some famous people, Henri Theil and Herbert Simon in the 1950s. And it's a characterization of linear quadratic optimal control problems. And then this was quickly noted by John Muth. John Muth knew this early. He read Simon very carefully. And he did some things with it. Okay, so you can read about that. That's a certain equivalence principle. And it gives rise to much of the power of linear quadratic dynamic control, dynamic programming, so-called certain equivalence principle. Okay, and that essentially, I'll tell you what Simon, this kind of history of thought, what Simon and Theil made about this, and Lucas and Muth picked up on this, is what this means is in these problems, you can separate optimal decisions, that's the UTs, from optimal prediction. I'm just going to leave that there. And Muth picked up on this. And here's what Muth picked up on. And here's the reason is what you do is you pretend as function of future stuff, pretending that you know it. You have perfect foresight. That's what this Simon said you could do. Oops, sorry about this. Okay, so Simon said you could do. And then what Simon said you could do is, what you're going to do is now you're going to replace future stuff with optimal predictions at time t of then future stuff. And if you combine them, that's how you can solve the problem. Now, this is special. This depends intimately on the LQ structure. But when it holds, it's really, really useful. And I think you might get a little hint of John Muth studied this carefully. And there's a famous book by Muth, Simon, Modigliani, and Holt, where this material is used extensively. And I think of it as setting the stage for rational expectations. I'm sure it set the stage. Okay. So I think I'm going to conclude this by just a little note about stability. And you may have wondered why, well, I'll talk about a little bit about stability. So the way this has happened is, remember I told you there were sufficient conditions for that iteration to converge. I said they were there, and I said they were not Blackwell's. And I said they were due to Leuenberger and some other people. Now, I'm not going to lead you through the mathematics of this. It's actually beautiful. But I'm just going to tell you a little bit about the philosophy of it. So the key thing is, so here is Leuenberger and other, but the key idea. It's to figure out jointly, well, the logic kind of goes like this. Here's kind of the logic. I think this is probably what the founders of this did. The first thing is they stare at that equation star. So remember what the equation star was. It mapped, it was iterations on this, really this counterpart of the Bellman operator. They stare at that. And they say, and they stare at all the components. And they say kind of like, they do a want operator. What would be required for this to converge? This is what they were doing. This is what I think they were doing. Okay, so then they said, well, it has to be true Remember, this is that eventually the decision maker wants to stabilize the state. And, you know, so what's kind of the state? It doesn't want it to explode. Okay, so what that means is, well, remember, our law of motion was this, xt plus b ut. But remember, we're using a decision rule that looks like this, and I'm going to put a t here, and we're going to think about t going out into the future. So what this means is I can substitute in, and this f is being solved from the Riccati equation. So I write this. Again, this is a loose argument. I write that. So that's the so-called closed loop system. So now I stare at this and I'll erase this. Well, I stare at this and I say, well, look at this thing. If this thing has eigenvalues greater than 1, xt is not going to converge. It's going to blow up. So what I want to happen is that the eigenvalues a minus bf, I want those to be t. Eventually, I want them to be strictly bounded by 1, in modulus. Otherwise, xt will diverge to, it will diverge. Okay, otherwise it'll diverge. And, you know, that might be the solution. Okay. But so that might be a problem. What that creates, if that happens, that creates difficulties for pj plus 1 to converge to p. This is their logic from staring at that equation. So then what they said is, let's make R and Q such that we know in advance the decision maker wants to drive ut toward, he wants to drive xt toward something finite, maybe 0. So now if they stare at this objective function, they say the following thing. If R is strictly positive definite, because of that minus sign, if R is strictly positive definite, this decision maker will never want to drive xt toward plus infinity in absolute value. Because in that case, this piece would diverge to plus infinity because it's a quadratic form. Similar argument for UTs. If the UTs aren't converging to something towards 0, this is going to go to plus infinity. So the conditions is the sufficient conditions, I should say, not the, but some sufficient conditions are that the decision maker wants to stabilize xt. And that implies he wants to stabilize ut. So those are what the sufficient conditions are. You notice the argument t is not a contraction. That won't work. But this argument will work, and it leads to some really beautiful applied math. For our problems, we're always going to have these conditions. Okay, they go under the name of detectability and realizability and observability. But I'm not going to go into them. I just want you to know that they exist. Okay. So I'm going to stop here with just a hint of what we're going to do next. And what we're going to do is revisit this problem and formulate it undergraduate style by taking a big Lagrangian. And I'll go back to the undiscounted problem. But now what I'm going to do is I'm going to put a Lagrange multiplier. I'm putting a 2 in front of it. I'm going to put a Lagrange multiplier. I'm going to call it mu instead of lambda on the constraint at time t. And what I'm going to do is I'm going to maximize with respect to ut xt plus 1. And I'm going to minimize with respect to the Lagrange multipliers. In other words, I'm going to apply the max-min Lagrange multiplier theory, and then I'm going to stare, and I'm going to figure some things out. And what we're interested in is how do the multipliers relate to P? And that's where we'll begin next time.